If we step back from our recent forays into the details of the machine and take a look at what we have, here's a pretty good block diagram of the structure of our register machine. We said we wanted to build a register machine that would implement eval, our explicit control evaluator. And we did this with a set of 7 registers, plus a set of primitive operations. And of course, those all need to be connected together, and we can do that using what's known as a bus structure, in which we have a wire that connects up all of the registers to all of the boxes, and allows us to arbitrarily place arguments from any one or perhaps a pair of different registers through one of these primitive operations, and then back around and into some other register. And of course, all of that will be controlled by the sequence of instructions and the program counter that tells us how to move things through one of those primitive operations and back around into a register. Now, in addition to those 7 registers and the operations that are going to manipulate things in them to cause eval to be implemented, we also needed to have a way of saving away state. We needed a stack, or if you like, a big collection of registers into which we could store temporarily values that we wanted to keep hold of until we needed them later on in a computation. So the stack, of course, has to also be connected both to the registers and to the primitive operations, so we can manipulate from there. Now, the last piece of the register machine is something we actually haven't talked about much yet, and that's something known as the heap. The heap is just a large collection of memory cells, or if you want to think of them that way, registers, into which we can store data structures. And in fact, we've seen in our evaluator that we have a big need for data structures. We use list representations, or pairs if you like, to represent expressions, to represent environments, to represent intermediate states of computation. So we need to also connect a very large set of places to store data in a heap that connects back into our register machine. And indeed, many of those abstract operations we used, manipulating the environment or manipulating the expression structures as tree structure, are going to take place in the heap, moving things in and out of the heap through the primitive operations and into registers for computation. Now, we've looked in detail at the 7 registers, the eval sequence of control that's built on top of those, the manipulation of the stack to create recursive calls and recursive procedures. So today we're going to finish up that last piece, the heap. Or if you like, we're going to look at how we create data storage methods and how we actually manage them in order to let the computation of eval take place. That is, how to create expressions out of tree structure, manipulate those expressions within the registers, and create environments that can also be manipulated the same way. We've already seen the idea of registers as places into which we can store values. To get the other pieces, we'll use the notion of a vector. And we saw this abstractly earlier in the term, but now we're going to make it more concrete. Most hardware supports the operation of random access to memory by specifying an index into a vector. So think of the vector as a long collection of registers, but with the property that to get to a location in the vector, one of those registers, one need only specify the number of slots from the beginning of the vector, also known as the offset, and one can then access that location in constant time. Notice this is different from a list where the time required would be linear in the index. I would literally have to walk my way down counting until I found the slot I wanted. Here, a vector consists of something that can be accessed in actual constant time. So more specifically, we'll need a base address, that is a pointer to some starting location in the memory, which we can label by a name such as my vector. We'll need an integer index or offset that tells us how many units or slots from that base address we want to get at things, and then we can store into those slots values themselves. And notice those values may be just numbers, but we'd also like them to be pointers to other kinds of structures. So they're going to have to be large enough to give us that freedom. Given that abstraction of a vector, or sort of the primitive way of dealing with these kinds of structures inside of memory, we need 2 ways of interfacing. First of all, in terms of standard scheme, we actually provide 2 primitive operations, a vector ref operation and a vector set operation. A vector ref operation takes a base address, that name of the beginning of that vector if you like, and an integer index, and will get us the contents of that slot, the appropriate number of offsets down from the base address. Vector set similarly takes a base address, a name for a vector, or rather a pointer to the beginning of a vector, an index or an offset telling us how many slots down to go, and a value to actually store into that particular location. And of course, we'll need a register machine version of this as well. And that says, for example, if we want to get the contents out of a vector, we'll have a primitive operation equivalent to vector ref that takes a vector, that is the contents of some register that tells us the pointer to a vector, takes an index, gets that contents out, and then stuffs it, for example, into some other register. If we want to do a set into the vector, we'll again specify the beginning of a vector by the contents of some register, as well as an index and a value, and it will do the register machine equivalent of vector set in scheme. Given this vector representation of memory, that is, we treat all of memory as just a big long collection of things in a vector that can be indexed in this way, it's very easy to implement the notion of a stack. We just use a pointer to indicate where the top of the stack is inside of that vector. That means we'll have to have a pointer to the beginning of the stack and then just simply an offset. And often we refer to that offset as the stack pointer, or SP. That stack pointer simply tells us where the top of the stack is, the last occupied cell, if you like. And if we want to put things onto the stack, we simply have to use the next available cell. Saving a register onto the stack now becomes quite simple. We first have a special register called the stack pointer, or SP register. It contains a number that points to the top of the stack, or the number of offsets, if you like, from the beginning of the stack into that vector. What do? We take that stack pointer contents, we add the constant 1 to it, we increase it by 1, and we put that new value back into the stack pointer register. That has basically moved the stack down by 1, taking up the next available element in this vector. And then, to put the actual contents onto that spot in the stack, we simply do a vector set. We take the stack register. That's going to have to be a special register as well that points to the beginning of the stack. We take the SP, or stack pointer register, and we simply move the contents of the register into that spot on the stack. Or said differently, we take the contents of the specified register and move a copy of those into the specified point on the stack. And restoring from the stack into the register just does the right thing as well. In other words, we take the beginning of the stack, we take the value of the stack pointer register, which tells us the offset to the top of the stack, the register that is the most available to us, and we simply take a reference from that, make a copy of that contents, and put it into the specified register. And having done that, we then pop one level off the stack. That is, we reduce the stack pointer register by 1, indicating that we now have a new stack pointer, and the stack is 1 less than what it was. Well, that takes care of the stack. It's pretty easy to do, just having this vector representation of memory around. What about the heap? Well, remember, conceptually, the heap is just a collection of free const cells, free pairs, and we should be able to create new ones as needed out of this collection. Now, large portions of the heap will simply be representations of list structure, expressions that we want to evaluate, or data structures we've built that we want to manipulate. But we're also going to have to be a little bit careful about how we create const cells out of the heap, since the heap will also hold most of our valuable information. In particular, remember what an environment is. It's a big collection of const cells that are glued together in appropriate ways, and those environments need to live and survive in the heap. We can't have us accidentally destroying elements of that cell structure by using the wrong cells in the wrong order. Okay, to build the heap, we will again use the idea of a vector. But now we're going to glue two vectors together in a very specific way. Imagine I have two vectors that I call the cars and the cooters. I can use a single index into these two vectors to represent a const cell. The location at index j in the cars would represent the car element, and the same location j in the cooters would represent the cooter element. Note that we'll need to have two more registers in our machine then to hold the base pointers to the beginnings of both of these vectors. And also notice, by the way, that we should also have added a pointer to the base of the stack in a special register, so that we have that capability as well. Given that idea of taking two vectors and gluing them together so that a single offset or a single index specifies both a car and a cooter, makes it very easy for us to actually implement our pair abstraction in the register machine. Now, a car operation has a very particular form. Before, we would have said assign into some register the car of some pair, where the car operation was treated as a special operation. Here we see we can be more specific. This actually becomes now a vector operation. We take the car's pointer, that is the register of the cars that points to the beginning of a big vector in the memory. We take the pair, which tells us an offset. It's just going to be an index now, a specific integer, and we use the vector ref operation to go to that spot and pull out the contents and put it where we want it to. That gets the car for us. And of course, cooter operation looks exactly the same, but now using the register, the cooters, that holds a pointer to the beginning of the second vector, and otherwise everything is exactly as before. Well, that says we can be very explicit about how we get the values out of existing pairs, how to get the car or the cooter of an existing pair. And of course, we can string together sequences of cars and cooters operations to get elements out of arbitrary tree structure. But what about the other direction? What about generating pairs? Or if you like, what does const do? Well, what we needed to do is to select a free slot in the vectors representing the cars and the cooters, and the method we use for doing this very much depends on how we're going to manage our memory, as we'll see very shortly. For now, consider the following straightforward idea. Let's allocate new cells in the memory in a linear fashion. So we'll add one more register to our machine, a register we call free, which points to the next available slot in the pairs vectors. In other words, free needs to hold an integer that tells us how many slots down to go from the beginning of both the cars and the cutters to find the next available cell. When we use const, that is, when we ask for a new pair, we'll simply use that new cell. We'll take the pair pointed to by free and use that to store in our values that we're consting together. And of course, having done that, we need to change free. And since we've chosen in this case to represent things in a linear manner, we simply increment free by 1, pointing to the now next available cell. Notice this is one choice of how we can structure memory, allocating things in a linear fashion. It's not the only choice, as we'll see shortly. For that particular choice of handling memory, we can now implement const directly in a register machine. Remember before, when we use const, we treat it as a primitive operation. We say given two values, we'll use const to generate the pair for us, and we can stick the result into some specified register. Now, we actually use the vector operations to make this happen. Notice what we have to do. It takes a little more work now because we have to be more careful. In particular, to generate a const, we start with the vector the cars, that is a pointer to the beginning of that vector. We use free to tell us how many slots down to go to find the next available spot. And into that spot, we store the first value. We do the same thing with the cutters, using exactly the same spot, since those two things together represent a pair. Since those represent a pair, that's what I'm going to stick into the register. Notice in particular what that does. The value of free, which is an index, an integer, is put into register. That actually makes sense because think about how I would get back out the car or cutter of that pair. My operation of car or cutter says start with the base pointer to either of those two vectors, use the value of the offset, the number, to go that many slots down to get the value out. And that's exactly what free is holding. Therefore, I've stuck it into register appropriately. Then, having done all of that, I need to increment free to point to the next available cell. And in this case, I just add 1 to the current value of free and store that away. The last thing we need to add to our system is a way of identifying primitive data. For example, if we create some list structure, then the cutter part of a const cell should point to some other const cell. But if we just store a number in the cutter, that is the index of the cell, how do we know that number is a pointer to a cell and not just a number? How do we tell the difference between a const pair whose cutter points to another const pair and a const pair whose cutter is just that number? Well, you actually already know the solution. We'll use a tag. Here we'll just use a very primitive kind of tag. And so for primitive data, what we'll do is take the bit structure representing an object, and we'll reserve a few bits, typically the higher order bits, to identify the kind of data. So for example, we might set aside 4 bits to be a tag, and use the remaining 28 bits either to represent the data value or to represent a pointer, that is an offset into the memory. For the 4-bit tag, we have an arbitrary choice here. We might, for example, choose to use the representation 0000 to indicate an empty list, and 0001 to indicate that this is a const cell pointer. That is, the remaining 28 bits that follow are an index or an offset to a particular pointer in the list structure. Whereas 0010 as a tag would indicate that this is actually an integer. That is, the remaining 28 bits should be treated as a number. 0011 might be a Boolean, and so on. Thus, for example, the representation 0001, followed by all those other things you see there, is a pointer to a const cell, because the tag says it's a pointer, and it's a pointer literally to the contents of the cell at offset 514. On the other hand, if we changed those 4 red numbers to 0010, this would indicate that this was the actual integer 514, not a pointer to some place in const memory. Of course, remembering that 0001 is a pointer and 0010 is an integer is a real pain. So we'll be a little more convenient about how we represent this. And in particular, we can use our representation of primitive data as simply a tag using a letter to indicate, for example, an empty list, a pointer, or a number, as well as the actual contents. And we're going to use that in a second to see how we deal with structuring memory. Given our little shorthand notation, we can now trace out the allocation of list structure within the heap. Suppose we've got an empty list structure to start with. We've got the cars and the cutters pointing to 2 vectors, and free is currently pointing to the 0 slot. Let's look at what happens if we evaluate the following little expression. Well, we know that list is basically just a sequence of const calls. And in fact, the first one to be evaluated will be the deepest one inside of the recursion. The others will become deferred operations until we get to them. And so, by our mechanism, this should go into the first available slot. In terms of our box and pointer notation, it says we'll have a little pair with 6 in the car and an empty list in the cutter, and we'll actually put the label P0 up on the top to indicate that that went into slot 0. It's a pointer to the pair P0. In terms of our car and cutter notation, we see that we put in the number 6 and the empty list. Now, that pointer P0 was the value actually returned by this const, and therefore we can do the next const, the first of the deferred operations, consting 7 onto that. That'll generate a pair in P1 because that's where free is pointing to. And again, we can update both our box and pointer representation and the vector representation. Notice how the cdr contains a pointer to P0, the pair in 0, meaning there's a tag saying this is a pointer to a pair, and the actual offset will be 0. And of course, we can complete the last const pair, putting that in P2, and as a consequence, putting the value 4 in the car at 2, and the pointer P1 to the other pair in the cdr part of pair 2. Notice also that the value of A is actually the pair P2, or if you like, the pointer to P2. It's a number that has 4 bits as a tag that says this is a pointer, followed by an offset that says the thing I want is 2 elements down. And literally we talk about A as having the value of that pointer. And in fact, we can see that if we look at the following example. Suppose we const A onto A. Well, const will use the next available cell where free points to, which is going to be pair 3. And what goes into the car? Well, just the value of A, which is the pointer P2. And what goes into the cdr? Also the value of A, which is still, of course, the value P2. So notice now in pair 3, both the car and the cdr have a representation that says what's stored there is a pointer to a pair, and it's the pair at index number 2. Well, what we've just seen allows us to have a means for allocating const cells from the heap. We've certainly been able to build something that will generate const cells as needed. Ideally, if our memory is large enough, we could just do this as needed and never have to worry. But of course, our memory is finite, and if we do enough of this, eventually we're going to use all of the const cells up. However, when that happens, not all of the cells in the memory are actually useful, and we may be able to take advantage of that. To see that, consider the following example. Let's define B to be a const of 1 and nil, which of course puts into the slot pointed to by free the number 1 in the empty list and increments free as we'd expect. Now, sometimes later, let's assume that we change the value for B. We set bang B to be a const of 2, 3. Const, of course, uses the next available cell, the thing pointed to by free, puts the number 2 and the number 3 into those spots, and then changes where free points to, moving it up. But notice that B has also changed. It used to point to pair 5, it now points to pair 6. Well, why does that matter? If you think about this in terms of box and pointer diagram, pair 5 is no longer accessible. That is, there's no way of referring to it, no way of getting to it from an expression that's available in the global environment, because nothing points into it. That similarly says in the actual structure of the cars and the cdrs that slot 5 contains things that are no longer accessible. We consider them to be garbage, meaning that the values associated or stored in those locations cannot possibly influence any future outcome of a program because they can't be reached by any way. Now that's an important point, so let's say it again. What are the cells that contain information that might possibly influence a future computation? Well, we know the only way we can reach an element of the structured memory here is through a sequence of car and cdr operations starting from values stored in the global environment. And if this particular pair no longer has a pointer from the global environment, we just changed it, we moved B from pointing to pair 5 to pointing somewhere else, then no matter what sequence of operations we take in terms of cars and cdrs starting from things stored in the global environment, we can't get to this cell. Since we can't get to this cell, it can't possibly influence future computations, therefore it's garbage. And of course what we'd like to do is say, can we gather that up? Can we reclaim such cells in order to have more memory available to us? Well, this filling up of memory with things that are actually garbage becomes a problem when we chew up enough memory that we run out. Consider the following simple example. This is for, of course, a very small memory, but the idea is the same even when we get to much larger memories. Let's assume that we just have 5 elements in our memory, and we've already defined C to be the list 8, 4, 7, 6. And so it's generated up a list structure shown here. C points to pair 3, and it has within it all of the list structure that creates the things we'd like to have. Now, let's evaluate a set bang of C to be a const of the cdr of C and the cdr of C. What does that do? Well, of course, evaluating const is going to use up the next free cell. It's going to use up pair 4, and ooh, that means that when we go to increment free, we've taken it beyond the bounds of the memory. And gee, that's too bad, because in fact we can actually build the structure we want. C points to pair 4. And to get the car of this, we take the cdr of C, that is, walk down and find the right pointer, which is in fact P0. And to take the cdr of this, we take the cdr of the original C, walking down to find that that should in fact be P1. So we can insert those pointers into pair 4, which is where C currently points, And of course, we also now smashed the old pointer for C. It used to point to pair 3, but it no longer does because we've changed that value. So in fact, pairs 2 and 3 are actually garbage. We can't reach them in any way, so they don't contain any useful values. And that's too bad, because our free pointer has just gone past the end of memory, meaning that we're out of memory, we have nothing left to allocate, yet in fact there are cells around that are still usable. And this then raises two interesting questions. Can we somehow detect which cells are garbage, which things are no longer useful to us? And having done that, can we somehow then figure out how to reuse those cells so that we can keep chewing up memory without having to run out of them by just simply because we've gone beyond the end of the currently available structure? Now, in fact, identification is easy, at least in principle. As we stated, the only cells in memory we care about are those that could possibly affect the state of future computations. And as we've also said, those are determined by the following idea. Remember that the state of the evaluator is completely captured by the contents of the registers of the machine plus the stack. So if we were to trace out sequences of car and coulter operations from those registers, this would lead us to the only cells that matter. Everything else is useless. So that would certainly allow us to identify those pieces and might give us a way of figuring out how to reclaim them. In terms of actually making that happen, we have a couple of different alternatives. And these are basically ways of dealing with the management of the storage of information. The first option really just puts the burden on the programmer. That is, it asks the programmer to explicitly worry about allocating and deallocating memory. And in fact, if you're familiar with programming in, say, C, you know that that happens. There are very explicit language constructs or procedures that free up memory as well as allocate memory. It gives control to the programmer, which is nice, but there's also a lot of potential for harm here. You get memory leaks when the memory is consumed but never recovered, and this is a very common bug in C programming. Similarly, you may accidentally overwrite a particular memory cell because you're not careful about how you're structuring the indexing into the const pairs that you want to use. An alternative, and in fact the one that is used by Scheme, is to free the programmer from having to worry about memory allocation and deallocation or recovery. It's basically to set up an automatic mechanism that finds and reuses memory. It's known as garbage collection, and it's used in things like Scheme and Java as a way of separating from the programmer the worries about memory allocation. What we're going to turn to now is seeing how we can make that happen inside of Scheme. The first method we'll look at for dealing with garbage collection is known as the mark sweep algorithm. And the idea is fairly simple. If we have our two vectors, the cars and the coulters, in fact here we've shown that simple little example we did earlier with the 5-element memory and the structure that we have in it corresponding to what we did in terms of creating C and then redefining it. Now, given those two vectors, we add in a third single-bit vector called the marks. And the idea is as follows. Those mark bits, which are all initially 0, are going to help us tell which things we want to keep. The idea is to start at the root of the good cells, at some beginning point of the cells we want, and then simply walk down that tree structure, the tree structure pointed to by that pair, following the pointers out of the car and coulter to subsequent pairs, and simply marking all the good cells. Once we've done that, we'll sweep together all the unmarked cells into a list of free cells. Gee, let's look at that to see how that works. For simplicity, assume our root, that is the beginning of the good cells, starts at C. So we start at point C, and it in particular points to the pair 4. So we put a mark in pair 4, indicating that that's something we want to keep. Having marked that cell, we then walk down the tree structure. That is, we take the car of pair 4, and we look at where it goes to. It points to pair 0, so we mark that as also being something we want to keep. We're now sitting at pair 0, but its car is just a number, its coulter is the empty list, so we can back up to where we were and take the coulter trail off of pair 4. It points to pair 1, and as a consequence we mark that as something we want to keep. And since the car of pair 1 is just a number, and the coulter of pair 1 points to something that we have already marked, aha! We don't have to keep doing that. There's no sense tracing anything further. In this case, we've traced out everything we possibly can, and we've marked all the useful cells. That means we can turn to the second stage. And the second stage is to sweep together all the unmarked cells. In fact, every cell that has a 0 in the marks is something we know we can recollect because we didn't reach it from anything useful. So to do this, we start an index beginning at 0, the beginning of the memory, and we set our free pointer to initially point to an empty list. And now what we're going to do is walk our way along. So our index, initially points to pair 0. And since the mark there is 1, we don't want to reclaim it. And as a consequence, we simply reset the mark to 0, saying it's something we want to keep. And we increment our index by 1, pointing to the next cell. Now index points to pair 1, but the mark there is also 1. It's something we want to keep, so we reset it to 0 and increment our index again. Now finally we've reached a cell whose mark is already 0, saying it's garbage. It's something we want to collect together. And as a consequence, we're going to stitch it together in the following way. We take the current value of free and we put that into the cdr slot. We literally smash what was there. It doesn't matter, it was just garbage. Putting, in this case, the empty list into the cdr slot at pair 2. And we then increment free to point to that actual pair. Free is now pointing to the first available cell, pair 2. And in the cdr of that cell is the pointer to the next available pair after this. And then we increment our index to the next pair. This pair is also garbage because its mark is 0. So we do the same thing. We take the current value of free, which was pointing to pair 2, and we stuff that into the cdr at this spot. That says the cdr here points to the next available cell, and we change free to now point to this cell. Notice what free points to. It says the next available cell is pair 3, and its cdr contains a pointer to the cell available after that, pair 2, whose cdr says, oh, empty list, nothing left. And we increment our index to go to the next cell. The mark for this cell is 1, saying it's something we want to keep. So we simply reset the mark to 0, and in this case, incrementing the index is going to take us beyond to the end of the memory, so we know we're now done. And again, notice free points to the next available cell in pair 3, its cdr points to the next available cell, etc. And in fact, the cdrs now stitch together the list of available cells, the things we've reclaimed. To actually implement a mark sweep algorithm is fairly straightforward. For the mark phase, we need a procedure with the following property. Given an object, that is, a pointer to something, it does the following. If that object's not a pair, it just returns false, saying I'm done with this. If, on the other hand, it is a pair, it checks to see whether the mark part of the object is equal to 1. If it's not, we set that mark to 1, saying it's something we want to keep, and then we recursively mark both the car of that object and the cdr of that object. Notice, for a pair, the object is just an integer offset denoting the cell location, the place I want to go to. But also notice that mark is doubly recursive. It's going to do a tree walk, in which, given a pair, it will mark down the car of that tree, and then come back and mark down the cdr of the tree, just as we saw in our little example. For our sweep phase, we just need a procedure that walks along the memory, sweeping things up. What does that do? Well, given some size of the memory, it takes the index I and says, gee, check to see if I'm equal to size. If I am, I'm done. If I'm not, then I do the following. If the mark at this location is on, or if you like, has the value 1, then I set the mark at that location to 0. I'm simply done. If, on the other hand, the mark is not 1, it's 0, then I do what I did in my previous little example. I convert that index into an actual pointer and then set the cdr of that pointer to whatever free currently points to. That's my global pointer to the things that are available. I then change free to point to this location, and I continue sweeping, doing the next cell. And I just do that until I reach the end of the memory. And of course, to glue it all together, my garbage collector in this case starts at the root, marks everything, and then sweeps, starting at 0, just capturing the ideas we did with our little example. So there's one memory management method, the mark sweep algorithm. Notice, of course, we have to actually go back and do a little extra work. We're going to have to change cons. Remember in our simpler example, cons just linearly moved its way through the memory. But here, the free cells are actually interspersed. And so, in fact, for this kind of memory management, we need cons to get the cell pointed to by the free list. It actually should say, give me that element in the free list, and that free list should then be updated to point to the next free cell. That is the thing in the cdr of the current cell. And this means, as before, we're going to have to do a little bit of manipulation of the car and cdr part of the cell. Well, that change to cons isn't that hard to envision, and that'll let us have this ability to stitch together these cells that are garbage in order to be reused. Notice, however, that the mark sweep algorithm also had this tree walk. We had this tree recursion in which, as we went along to do the mark, we had to mark down the car and cdr parts of the tree. And how do we implement that? Oh, we need a stack. And in particular, we're going to need a separate stack, a stack different from the stack associated with the evaluator. So we'll have to allocate one other piece in our memory, a stack specifically set aside for garbage collection. Well, if we're going to need a stack, we're going to need to have some memory set aside for it. And one of the questions is, how deep might that stack actually be? And the answer is, well, it could actually be as deep as the number of cells in the heap. And we'll leave it to you as an interesting question to think about what kind of data structure would actually cause us to chew up a huge amount of information on the stack for the garbage collector in order to do the mark stage of that mark sweep algorithm. Our second method for garbage collection is known as stop and copy. Here the idea is that we take our memory and we split it in two. In one half, the so-called working half, we have again two vectors for the cars and the cooters. And in the other half, the so-called free half, we have two other vectors called new cars and new cooters. We keep filling up things in the first memory, the working memory, in the linear fashion we did before until we end up at the end of that memory. We run out of memory. At that point, we want to stop and copy. Literally, we want to stop the machine and copy all the useful information from the first memory, the working memory, into the free memory, and then go back and switch the roles. So when we're ready to do the stop and copy, that is, we've run out of memory and we need to copy things, the first phase is that we're going to move all the good cells into the new memory, leaving behind pointers, so-called forwarding pointers, that tells us where we have moved that cell into the new memory. Let's assume that our root pointer, that is a register that points to the beginning of the useful structure, points to element 4 in this memory. This is exactly the same little list structure we had before. We called it C in that case, but now it's simply pointing to pair 4. Well, the first thing we do then is copy what's in pair 4 here into the free element, or the first element available to us in the new memory, putting a copy literally of that structure into pair 0 in the new memory. And having copied that over, we put a marker as to where we put it in the cooter part of this cell, a pointer to P0 in the purple memory if you like, and in the car part of this cell, we put in what's known as a broken heart for historical reasons that says that this element has been moved to the new memory, and the cooter tells us where it was moved to. Having moved that first cell over to the new memory, we now take its car and trace out the structure from there, deciding whether we need to move those things as well. Now the car of that first moved cell points back to a pair in the original memory, to pair P0 in fact. So we're going to move that over, and we update the structure in the old memory. We've moved this cell over, so we put a marker as to where we put it. It's now in P1 in the purple memory, and we put the broken heart in to indicate that we've moved it over to this new memory. Now, if we look at pair 1 in the new memory, there's nothing to move here because we just have a number and an empty list. So we can back up to where we were, which was P0 in the new memory, and now trace things off of the cooter part of that thing. That points to pair 2, or rather pair 1, in the old memory. So we move that pair over to the next available cell in new memory, and update the old memory with a broken heart and a forwarding pointer. Now, if we look at pair 2 in the new memory, we can see that its car is just a number, and its cooter is a pointer. But it's a pointer to something that already has a broken heart in it. It's a pointer to a structure that's already been moved. And to avoid looping forever, we don't need to go back and trace that portion. Having done that, we're now done with everything we've moved over. We have nothing further to trace, so we've actually moved all of the useful cells into the new memory. Now we're ready for the second phase of this operation. We've moved everything useful over into the new memory, but the pointers there are pointing back to old memory. They're pointing to the broken hearts that tell us where to find things. So simply all we need to do is now update the pointers and the move cells to reflect the new locations, to actually say where they point to in the new memory rather than this indirect through the old memory. So starting with the first cell of new memory, we start in its car and change its pointer from the old value in the old memory, replacing it with the pointer, the forwarding address, the place it points to in the new memory. We do the same with the cooter of this cell. We look up its old value in the old memory, or rather its forwarding address in the old memory, and replace it directly with that in the new memory. Then we move to the next cell in this new memory and do the same thing. Numbers don't have to change and empty lists don't have to change. And when we get to the next cell, we simply update those things. Numbers are the same, but the old pointer gets replaced with its forwarding address to the new pointer. And having reached the end of the new cells that we want to deal with, we're now done. So we can in fact now swap the roles of these two halves of memory. We change our root pointer to point to the beginning of this new structure, the place where we moved that cell. We have our free pointer point to the beginning portion of the memory that is now available to us, and we can carry on. Const will use what is currently pointed to by free. We'll increment by 1 and keep doing that until we run out of memory in this memory, and then we'll do exactly the same thing. We'll stop and copy back into that original memory, reverse the roles, and keep on. Now in the mark sweep algorithm, we never moved the actual cells that contained useful information, so we were guaranteed that the list structure we had before we did the garbage collection was exactly the same when we were done. Here we've actually moved things around, so the only thing we have to do is make sure we haven't changed anything. And in fact, if we start at the root, which is where C was, if we trace out the structure in the new memory, we'll get the box and pointer diagram shown here, and we can check that that is in fact exactly the same box and pointer diagram as what we had originally. The pairs are different, the actual values of where they're stored are different, but the structure, and therefore the things we'll get out with car and cooter operations, have not changed. It's been preserved, which is exactly what we want as we've done this stop and copy garbage collection. So here then is a description and a little more algorithmic detail of what we just did. Our stop and copy algorithm is very straightforward. We set the free and scan pointers to the beginning of the new memory when we're ready to stop and copy. We move the root pair over to the new memory and adjust its pointer to the new location, incrementing free as necessary. And then we go back and mark old pairs by putting that forwarding pointer, that broken heart in, telling us where we move things through. And the basic cycle is to simply trace the pointers in the car encoder of the cell pointed to by scan back to the old memory. We relocate each one. If it's a forwarding pointer, we just use that address to update the pointers. And if it's not a forwarding pointer, we copy it into the free pair, increment free, store a forwarding pointer, and update the pointers. And go back and increment scan. And we keep doing that until scan actually catches up to free, telling us that we're stopped, we've done everything we have to move. Now, we can actually implement that. And here's a scheme description of that code. The GC copy is going to do the following. Given a pointer scan, it's going to run through that little cycle we just described. If scan's not equal to free, then I still have something to do. And in particular, what do I want to do? Well, I'm going to change the car of what scan currently points to be whatever the forwarding reference is for the current thing in there. And I'm changing the cooter of scan to point to whatever the forwarding reference for the cooter of that thing is. And then I move on. And forward, well, you can look it through, but you can see it just does the right thing of actually walking its way along, finding the right piece to point to. So what's the relationship between stop and copy garbage collection and mark sweep? And basically there's some trade-offs. The big disadvantage is that in stop and copy, we require double the memory. Or if you want to think of it, for a fixed amount of memory, we only ever have half of it available at any one point in time, because we have to reserve the other half for copying. On the other hand, there's an advantage here. And the advantage is that this garbage collector compacts things. That is, when we do the stop and copy, it puts all the connected cells at the front of the memory, which both makes consing much more efficient, because it just linearly moves things along. And if we have things like paging, something you'll see later on in your courses here in Course 6, that means that the things we want to get at are actually more easily accessible. So what we've seen then is that we can actually build our list-structured memory out of a very simple construct. Given this idea of a vector, a string of elements in the memory indexed by an integer with the ability to get to that point in constant time by simply offsetting from some base location, we just take two of those and glue them together to give us the idea of a pair. And of course the impact on the language is that we have a very flexible compound data mechanism. Everything we've seen in Scheme can be glued together with list structure or tree structure built out of list structure, which all relies on having that ability to const together a pair of elements. Since we're going to use numbers to indicate indices or offsets into that list structure, we have to be a little more clever. And we use a tagged memory architecture to do that, meaning given a number or given a bit representation of some piece of data, we reserve the small set of bits at the front to indicate a tag. Is this a number? Is this an empty list? Or is this actually a pointer into a pair? And that tells us how to, in fact, interpret the rest of the data structure. One of the nice things about this in terms of the language, by the way, is that allows us to do some amount of runtime type checking. We could actually check at runtime to make sure the structures we have are the right source by looking at the types. And this also provides a great deal of flexibility in how we build and manipulate the language. And finally, we've seen that given that we were going to build the language out of this simple pair structure, we have a nice way of being able to handle reallocation of that memory. We're going to do garbage collection to find those cells we no longer need and reuse them, giving us the impression of having much more memory than we actually have. While there's some cost in terms of efficiency by doing garbage collection, there's a very nice impact on the language. Namely, we free up the programmer from having to do the memory management directly. And that avoids lots of the constant problems one has in those languages, especially when we get memory leaks of accidentally using up more memory than we want and not being able to reclaim it. Here, the machine takes care of it for us automatically.